Pluto is a baffling bantam planet that exists today at the outer horizons of our immediate world. The cosmic community is generating energy within the continuity reports of the universe. These reports imply that a possible encounter with Neptune has caused concern among space enthusiasts and researchers alike. Prestigious experts, such as Michio Kaku and Neil deGrasse Tyson, have sounded alarms about the likely results of this conflict between the gods. But where did Pluto end up? Is it on a path of impact with its distant neighbor? And what would such a collision mean for us on Earth? Let us examine this phenomenon once more. Pluto was once regarded as an unquestionable planet but was later given the new designation of a bantam planet due to its unique orbit. Despite this modification, it continues to captivate astronomers and researchers. Ongoing forecasts from well-known scientists draw attention to the proximity of Pluto's orbit to that of Neptune. These experts warn that any potential interaction between the two planets could pose a serious threat. Pluto's journey around the Sun is marked by its superior characteristics. Its orbit spans a staggering 248 years, and since its discovery in 1930, Pluto has not yet completed a full revolution. This fact enhances its intrigue. Its unusually elliptical orbit is a departure from the nearly circular paths of major planets. Additionally, Pluto's orbit is inclined at 17 degrees to the ecliptic plane, a much steeper angle compared to other planets. One important aspect of Pluto's orbit is its intersection with Neptune's path. For approximately 20 years per orbit, Pluto ventures closer to the Sun than Neptune, defying expectations about their relative positions in the solar system. So why hasn't an impact occurred between Pluto and Neptune? The answer lies in the forces of gravitation exerted by other planets. The analysis of Pluto's orbit began shortly after its discovery and posed an incredible challenge for cosmologists. Unlike most planets, whose orbits align relatively closely to the ecliptic plane, Pluto's orbit is uniquely inclined and eccentric. The mystery deepened when it became clear that Pluto's orbit crosses Neptune's path. The stability of Pluto's orbit amidst these complexities serves as proof of the intricate nature of space mechanics. The three-body problem in space involves calculating the motion and gravitational interactions between three celestial bodies, such as Pluto, Neptune, and the Sun. This problem explains the complex exchange of their travel routes. Astronomers use concepts like libration and the swaying of the KBOs, Kuiper belt objects, to unravel this cosmic mystery. Libration, a gravitational phenomenon responsible for maintaining planetary orbits, plays a key role in the Pluto-Neptune system. This term refers to the fact that when Pluto passes near Neptune, its orbit remains at least 90 degrees away from Neptune's, crucially preventing potential collisions. Libration ensures that when Pluto comes close to Neptune or other large planets, it predominantly stays above or below their orbital plane, providing an additional safety mechanism. The KBO sway explains why Pluto's orbit around the Sun appears irregular but remains stable over time. Despite the apparent randomness, mathematical simulations from the late 1980s demonstrated that Pluto's orbit, while seemingly chaotic, actually maintains long-term stability. Even minor changes in initial conditions could lead to significant shifts over millions of years. However, Pluto's special orbit remains stable on extremely long timescales. Computational models have improved our understanding of how massive planets like Jupiter, Neptune, and even Saturn influence Pluto's motion. A unique relationship exists between Pluto, Neptune, and the Sun. For every 3 orbits that Neptune completes, Pluto completes 2. This resonance contributes to Pluto's orbital stability. Jupiter's immense gravitational pull also plays a substantial role, while Saturn, despite its smaller influence, also contributes. Through in-depth research, scientists have demonstrated that the combined gravitational effects of Neptune, Jupiter, and Saturn ensure Pluto's stable movement over billions of years. These interactions are crucial for preserving order in the solar system. Without these gravitational stabilizers, the solar system would be more susceptible to chaos, potentially resulting in planetary ejections or collisions. Pluto's orbital mechanics are especially significant in discussions about a potential future crash with Neptune. Understanding these interactions offers a clearer perspective on the dynamic nature of our planetary system. Pluto's case highlights how seemingly unstable orbits can reach a form of equilibrium through the intricate interplay of gravitational forces. Constant monitoring and investigation of these celestial phenomena are essential for understanding our place in the universe. The study of space's depths frequently reveals the unpredictable nature of celestial bodies. Pluto's orbit is a prime example of this eccentricity. The concept of orbital disorder demonstrates the delicate balance between a celestial body's initial conditions and its long-term trajectory. Even slight variations in Pluto's position or speed can dramatically alter its long-term orbit. Simulations have been instrumental in helping researchers understand how Pluto moves in space. By making small adjustments to these models, scientists can observe how even minor changes can have significant consequences. In the late 1980s, simulations uncovered an intriguing feature of Pluto's orbit. Despite libration and other stabilizing factors, Pluto's trajectory can still exhibit irregularities. Even the smallest initial difference in Pluto's position or speed can lead to significant orbital changes over time. Despite this, Pluto's orbit maintains a form of structured chaos, persisting for billions of years. Beneath its seemingly erratic nature, Pluto follows an ordered path around the Sun. Predicting the future paths of celestial bodies, particularly those with unusual orbits like Pluto, remains a challenge. The inherent unpredictability of these systems makes long-term forecasts difficult. While simulations based on mathematical models help us predict future motions, they also highlight the limits of our predictive capabilities. These models heavily depend on precise initial conditions, and even a small error can lead to drastically different outcomes. The chaotic nature of celestial orbits like Pluto's reminds us of the universe's constant change. Despite our progress in understanding space, Pluto's case highlights how much we still have to learn. Studying the gravitational effects of massive planets on Pluto provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet influence the direction and stability of other celestial bodies. In light of these complex interactions, prominent astrophysicists continue to express concerns about a possible collision between Pluto and Neptune. Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, especially regarding Pluto. Tyson, known for advocating Pluto's reclassification as a dwarf planet rather than a full-fledged planet, provides insightful ideas on how our understanding of celestial mechanics is constantly evolving. As we delve deeper into Pluto's orbital dynamics, it becomes clear that its stability is not purely coincidental. The gravitational forces of the solar system interact in such a way that Pluto avoids catastrophic encounters with Neptune. However, despite these safeguards, Pluto's long-term trajectory remains a subject of intrigue. One of the most significant aspects of Pluto's motion is its position within the Kuiper belt, a vast region beyond Neptune filled with icy bodies and dwarf planets. The Kuiper belt is a remnant of the early solar system, a collection of celestial debris that never coalesced into a planet. Pluto, as one of its most prominent members, provides crucial insights into the formation and evolution of our cosmic neighborhood. Recent advancements in astrophysics have allowed scientists to refine their models of Pluto's movement with unprecedented accuracy. High-precision telescopes and space probes, such as NASA's New Horizons, have provided a wealth of data, enabling researchers to study Pluto's surface composition, atmosphere, and geological activity. These discoveries have deepened our understanding of how external forces, such as solar radiation and interstellar particles, contribute to Pluto's long-term stability. Furthermore, the role of planetary migration in shaping the solar system cannot be ignored. Some theories suggest that Neptune itself may have shifted its position over millions of years, influencing Pluto's orbit in ways that are still being explored. This concept of planetary migration adds another layer of complexity to the discussion, raising the possibility that Pluto's current trajectory is a result of ancient gravitational disturbances. Looking ahead, astronomers continue to monitor Pluto's movements to detect any unexpected variations. While current models indicate that Pluto and Neptune are unlikely to collide, the ever-changing nature of the universe means that even slight perturbations could alter their courses over vast timescales. The study of celestial mechanics remains an evolving field, where new discoveries can reshape our understanding of planetary dynamics. Pluto's case serves as a reminder that the cosmos is a delicate balance of order and chaos. Its orbital dance with Neptune is a testament to the intricate gravitational relationships that govern our solar system. While concerns about a collision may be largely speculative, the exploration of such possibilities pushes the boundaries of our knowledge and fuels humanity's ongoing quest to understand the universe. As we continue to unravel the mysteries of Pluto and its place in the cosmos, one thing remains certain: the study of celestial bodies, no matter how distant, offers invaluable insights into the fundamental forces that shape our world. Whether Pluto is classified as a planet, a dwarf planet, or a bantam planet, its story is far from over. Tyson is aware of how space-related events and discoveries capture the public's attention. He sees events like Pluto's renaming and its peculiar orbit as opportunities to engage the public's imagination and interest in the universe by discussing the dynamic and sometimes illogical aspects of space. Tyson's mechanics encourage a more in-depth enthusiasm and comprehension of the cosmos. Neil deGrasse Tyson opens a window for the general public to wonder at the miracles and mysteries of the universe. Working alongside other researchers, Tyson actively warns the public about the potential risks of Pluto's unusual orbit. Following extensive Pluto research, he has questioned whether the three-body problem could pose a serious threat, implying an encounter with Neptune may have been long overdue. Tyson emphasizes how such a collision could perturb the equilibrium of the universe and result in disastrous outcomes, extending even to Earth. A collision between Pluto and Neptune would be a rare and catastrophic event. Our solar system would explode, likely releasing a huge amount of energy, disintegrating Pluto due to its smaller size and cold nature. The debris from the collision could spread throughout the solar system, posing dangers to other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specifics of the collision. A well-known and renowned theoretical physicist, Michio Kaku, offers a fascinating perspective on this scenario. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics provide an in-depth understanding of phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital elements of celestial bodies like Pluto, according to Kaku, offers important insights for future space missions. This knowledge can aid in better navigating the solar system, effectively preparing for potential dangers, and making plans for trips to the outer reaches of our planetary system and beyond. Kaku stresses that the lessons obtained from studying Pluto's orbit can be used to investigate other celestial bodies, providing a blueprint for approaching and understanding distant worlds. When discussing the physics of planets, Kaku often highlights the profound connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated events but are tied to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to grasp these principles at the most fundamental level. He proposes that considering the complexities of planetary motions, like Pluto's orbit, can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also explored the possibility of planetary collisions, relating them to his theories about the cosmos. In the event of a Pluto-Neptune collision, it would be a significant event in astronomy, providing a unique observational opportunity that could contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, seeks to unify the primary forces and interactions of matter in the universe. A collision of this magnitude in the solar system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental forces and particles in extreme circumstances. A key focus in string theory is also the gravitational waves produced by such an impact, which could provide valuable data for testing predictions of string theory related to gravity in spacetime. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be significant, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a significant example of celestial mechanics, demonstrating both stability and chaos within our solar system. The extraordinary features of its orbit, influenced by gravitational forces, particularly from nearby Neptune, emphasize the intricate and dynamic nature of the universe. Space holds numerous secrets, and the three-body problem is just one of them. There are other potential catastrophes that scientists anticipate, but the probability of planetary collisions in space is very low. However, it is not entirely impossible. Planetary orbits are influenced by various factors, including gravitational interactions explained by the three-body problem. In some space systems, like TRAPPIST-1, which has 7 Earth-sized planets, gravitational forces create a rhythmic pattern called orbital resonance. Over time, these resonances can make planetary paths less stable, possibly resulting in collisions. Despite the crowded nature of systems like TRAPPIST-1, impacts are not currently happening. Researchers closely monitor these systems to understand how planets affect each other's orbits, especially when they are in close proximity. This information aids in our comprehension of planetary motion in space. Maverick planets, or rogue planets, drifting through space without orbiting a star, add another curious element. These planets, once part of a star system, are ejected due to gravitational disturbances or other cosmic events. For example, the close approach of another star or dynamic instability in a system can cause these rogue planets to travel vast distances, potentially reaching areas far from their original location. During their journey, there is a possibility that a rogue planet could enter another planetary system. If this happens, there is a slight chance of it colliding with a planet in that system. However, given the vast and mostly empty nature of space, the likelihood of a rogue planet directly impacting another planet is extremely low. The immense distances between stars and the relative rarity of rogue planets make such collisions even less likely. Furthermore, stable planetary systems far outnumber rogue planets, making these encounters extraordinarily rare. The study of celestial mechanics and planetary interactions remains a crucial area of astrophysics. Scientists use advanced simulations and observations to understand how planetary systems evolve over time. These studies not only provide insights into our own solar system but also help in predicting the stability of exoplanetary systems. One of the key challenges in celestial mechanics is predicting long-term orbital stability. Small gravitational perturbations over millions of years can lead to significant changes in planetary orbits. This is why understanding the three-body problem and other complex gravitational interactions is essential. The orbits of planets like Pluto, which experience gravitational influences from multiple bodies, serve as valuable case studies for these phenomena. Moreover, studying these interactions has practical applications. As space exploration advances, future missions to the outer solar system and beyond will require precise navigation through gravitationally complex regions. Spacecraft trajectories often rely on gravitational assists from planets, a technique that uses a planet's gravity to alter the spacecraft's speed and direction. Understanding planetary motions at an intricate level improves mission planning and efficiency. In addition to planetary collisions and orbital mechanics, astrophysicists also study how celestial events influence the broader cosmic environment. For instance, when large objects collide in space, they can produce high-energy radiation, gravitational waves, and even trigger changes in planetary atmospheres. If a Pluto-Neptune collision were to occur, scientists would closely observe the event using telescopes and space probes to gather data on the physics of high-energy impacts. Beyond our solar system, astronomers continue to search for exoplanets and study their orbital dynamics. The discovery of exoplanets in habitable zones, regions where conditions could support liquid water, has fueled interest in planetary stability and habitability. By studying Pluto and its interactions, researchers refine models that apply to exoplanetary systems, improving our understanding of planet formation and evolution. As humanity advances technologically, the potential for space colonization and interstellar travel becomes a more serious topic of discussion. Understanding celestial mechanics will play a fundamental role in determining the feasibility of long-term space travel. Future missions may need to account for gravitational anomalies, rogue planets, and potential hazards like asteroid collisions. Ultimately, the study of space is not just about understanding distant worlds but also about preparing for humanity's future in the cosmos. Scientists like Tyson and Koku contribute to this knowledge, bridging the gap between theoretical physics and practical space exploration. Their insights inspire new generations of researchers, engineers, and space enthusiasts to explore the vast and mysterious universe.